Good morning, everyone. Welcome to the class. This is our third lecture. The topic of this lecture is mechanical properties of materials. Before we begin this course, I want to make one thing very clear. We study mechanics not to solve equations and not to test how fast you can manipulate symbols. We study mechanics to understand how the physical world actually works and to use that understanding to make reliable engineering decisions. Or in one sentence, we study mechanics not to solve equations, but to empower the dreams of flight with the certainty of science. Let me explain what I mean by that. When you look at a modern aircraft, what you see is speed and efficiency, but what makes flight possible is not just aerodynamics. It is materials, and nowhere is more obvious than a jet engine, which is often called the crown jewel of human industry. This course is designed to help you build that intuition. Equations are tools. They are important, but they are not the goal. The goal is to understand how stress, strain, deformation, and failure emerge from physical mechanisms and how they guide engineering design. This is a jet engine, specifically a turbofan engine. At the front is his giant fan. During takeoff, these rotating blades push 1.3 tons of air backwards every second, and around 10% of that air gets compressed. The compressors force the air into increasingly narrow chambers. They compress the air to about 50 times atmosphere pressure. This compressed air is then forced into the combustion chamber, where fuel is sprayed in through a ring of nozzles and ignited. That chemical reaction gives off a lot of heat, so the temperature jumps to around 1,500 degrees Celsius. So now you have got this high-pressure gas from the combustor that just want to expand, and also got an incredible amount of thermal energy. But between the combustion chamber and the outside air is the turbine blades. So in order for the gas to expand and get out, it needs to push these turbine blades out of the way. And in pushing those blades, that is how it transfers its energy to the engine. This is where all the power really comes from. As the gas rushes through the turbine and nozzle, its pressure drops from around 50 atmospheres down to 1, and it expands by almost 20 times. And that spans these turbine blades up to 12,500 revolutions per minute. All the turbines are connected in the jet engine, the fan that is pushing all that air backward, and all those compressors that squeeze the air down. All of this is powered by the turbines back here. That's kind of funny, really counterintuitive way to think about an engine, right? It's what's happening in the back that's actually driving everything up front. As the hot exhaust gas is shot out the back of the engine, it pushes the engine forward. That generates thrust. But did you know that in a modern passenger jet, this accounts for less than 20% of the thrust of the engine? The vast majority of the thrust just comes from that big fan at the front of the jet. Remember how only 10% of the incoming air gets compressed? The other 90% bypass all that. It's simply propelled backward by the fan. It goes right around the gas of the engine and comes straight out the back. The fan pushes that air backwards, so the air pushes the fan forwards. That's how you get 80% of the thrust. It's basically a huge propeller. So why not compress all the incoming air and put it all through the combustion chamber and turbines? The answer is energy efficiency. Remember that the impulse pushing the plane forward is equal to the change in the momentum of the air backwards. For example, you could push twice as much air back, half as fast, or you could push half as much air back, twice as fast. Both will generate the exact same impulse, but it takes 4 times as much energy to speed up the air in the second case, and a lot of that energy is just wasted in the thrust. So ideally, you want to push as much air backwards as possible with only a small change in velocity. That's why jets have gotten bigger and bigger over the years. But there is another major factor when it comes to engine efficiency, and that is temperature. But there is a fundamental limit to how much work many heat engine can get from that. It's called the Carnot efficiency. It's equal to 1 minus the temperature of the cold outside air divided by the temperature of the hot gas inside the combustion chamber. At cruising altitudes around 35,000 feet, the outside air is around negative 55 degrees C, which is around negative 67 degrees F. So looking at this, you can improve the efficiency of the engine by raising the temperature in the combustion chamber. One problem with that is it turns the inside of the jet engine into one of the harshest environments we have ever built in which machine has to survive. Remember, the turbine blades are also spinning at 12,500 RPM, with the tip of each blade slicing through the air at nearly 1,900 kilometers per hour. Now, every blade wants to fly straight, but it's forced to spin in a circle, which means something has to be constantly pulling it inwards. That is the centripetal force. If you take a representative 300-gram blade, the force calculated is around 200 kilonewton. That's roughly the weight of 2 campus buses tugging on each blade as it spins. Therefore, the material must be strong enough to carry this load, as well as not deform too much under both the load and the high temperature. Image a block of material to which we apply a force F. The force is transmitted through the block and is balanced by the equal opposite force on the base of the block. We can replace this base by the equal and opposite force F, which acts on all sections through the block parallel to the original surface. The whole of the block is said to be in a state of stress. The intensity of the stress is measured by the force F divided by the cross-sectional area A of the block face. This particular stress is caused by a force pulling at right angles to the face. We call it the tensile stress. Suppose now that the force acts not normal to the face but at an angle to it. We can resolve the force into 2 components, one Ft normal to the face and the other Fs parallel to it. The normal component creates a tensile stress in the block. The other component, Fs, also loads the block, but it does it so in shear. The shear stress in the block parallel to the direction of Fs is given by tau equals Fs divided by the cross-sectional area A. For more complex stress states, stress tensors are typically used. In 3-dimensional space, the stress tensor is a 3x3 square matrix. Each element represents the normal stress or shear stress acting on different surfaces of a cube, as shown in the image in the lower left corner. Typically, the 3 elements on the diagonal represent the normal stress in the x, y, and z directions, while the off-diagonal elements represent the shear stresses in the corresponding directions. We will discuss this stress matrix or stress tensor in detail during the later half of this semester. Materials respond to stress by straining. Under a given stress, a stiff material, for example steel, strains only slightly. A floppy material strains much more. The modulus of the material describes this property, but before we can measure it or even define it, we must define strain properly. The kind of stress that we call a tensile stress induces a tensile strain. If the stressed cube of a length L extends by amount U parallel to the tensile stress, the normal tensile strain is calculated by U divided by L. When it strains in this way, the cube usually gets thinner. The amount by which it shrinks inwards is described by Poisson's ratio, which is the negative of the ratio of the inward strain to the original tensile strain. A shear stress induces a shear strain. If a cube shears sideways by an amount of W, then the shear strain is defined by gamma equals W over L, which is actually tangent theta. Theta is the change in angle. Or sometimes it's called the angle of shear, and L is actually the edge length of the cube. Since the elastic strains are almost very, very small, we may write to a good approximation gamma approximately equal to theta, because tangent theta equal to theta when theta is very, very small. Let me explain why we use stress and strain instead of just force and displacement. First, think about bending steel bars. Image several bars. They are all made of the same steel, but they have different cross-sectional areas. What do we observe? The larger bar needs more force to bend. The thinner bar bends more easily. So here is the key question. Does that mean the thinner bar is weaker? Not necessarily, right? The difference comes from size, not from the material itself. Force depends on how much material you have, so force alone cannot tell us how the material behaves. This is why we introduce stress. Stress is the force divided by area. It removes the effect of size and lets focus on the material response. Now look at strain. Think about stretching two bars by the same amount, say 1 millimeter. Again, both bars are made of the same steel, but this time they have different initial lengths. Bar A is very long, bar B is very short. Even though the displacement is the same, the material experience is very different. For the long bar, the strain is very small. For the short bar, the strain is very large. So do they deform in the same way? No. Displacement depends on length, but strain is displacement normalized by length. This is why strain tells us how much the material is actually deforming, independent of geometry. So this is the main idea. Force and displacement depends on size and geometry, but stress and strain do not. Stress removes the effect of a cross-sectional area. Strain removes the effect of length. Once we do this, what remains is the true material response. Finally, let me mention the sign convention shown at the bottom. By convention, tensile stress is positive, and elongation strain is also positive. Compression would be negative. This is just a convention, but it is important to be consistent. So from this point on, when we talk about material behavior, we will mostly always think in terms of stress and strain, not force and displacement, because stress and strain tell us what the material is doing, not just how big the structure is. The degree to which structure deforms or strains depends on the magnitude of an imposed stress. The Hooke's law describes the relationship between engineering stress and engineering strain for elastic deformation. For most metals that are stressed in tension and at relatively low levels, stress and strains are proportional to each other, and the coefficient is called Young's modulus. This modulus may be thought of as stiffness or material's resistance to the elastic deformation. The greater the modulus, the stiffer is the material. or the smaller is the elastic strain that results from the application of a given stress. The modulus is an important design parameter for computing elastic deflections. Now that we understand stress and strain, we can talk about what really matters in engineering: mechanical properties. Mechanical properties describe how a material behaves when it is subject to mechanical stresses. In other words, they tell us what the material will do when we pull it, push it, bend it, or twist it. These properties include several important concepts. For example, elastic moduli, such as Young's modulus. They tell us how stiff a material is, how much it resists elastic deformation. Then we have strains, which tell us how much stress a material can carry before it yields or fails. We also talk about ductility, which describes how much plastic deformation a material can go before fracture. And finally, hardness, which is related to resistance to localized deformation, such as indentation or scratching. Together, this property defines the mechanical personality of a material. Now, here is an important point, highlighted on the slide as a dilemma. The mechanical properties that are desirable to a designer are not always describable for manufacturing. For example, materials with very high strength are often difficult to machine, form, or shape. They may require higher forces, special tools, or more complex processing routines. So, there is always a trade-off. From a design perspective, we want materials that are strong, stiff, and reliable. From a manufacturing perspective, we want materials that are easy to process, easy to shape, and cost-effective. Engineering materials are therefore chosen not by maximizing a single property, but by balancing multiple requirements. An understanding of many of the physical properties of the material is enhanced by a knowledge of the interatomic forces that bind the atoms together, or in other words, the springs between atoms. Perhaps the principles of atomic bonding are best illustrated by considering how two isolated atoms interact with each other. At large distance, interactions are negligible because atoms are too far apart to give an influence on each other. However, at small separation distance, each atom exerts force on the others. These forces are of two types: attractive, denoted by Fa, and repulsive, denoted by Fr. And the magnitude of each depends on the separation or interatomic distance. When the atoms are too close to each other, the overlapping of electron clouds causes electrons that originally belongs to different atoms to compete for the same space, thus repelling each other. When they are at intermediate distance, the formation of interatomic bonds, such as ionic bonds, metallic bonds, and covalent bonds, leads to a more rational electron arrangement, thereby lowering the total energy of the system. System naturally tends towards lower energy states, which therefore creates an attractive force. Integrating these two forces yields the energy of the system. If we can obtain the system's energy as a function of the interatomic distance, we can roughly deduce many of the material's mechanical properties. Using sodium chloride as an example, its interatomic potential energy can typically be written in this form. Please note that the attractive potential energy here is represented as Coulomb attraction, which is a very simplified expression. The actual interatomic potential energy may be far more complex than this form, but since here we just use it for illustration, so it's acceptable. On an atomic scale, macroscopic elastic strain is manifested as small changes in the interatomic spacing and the stretching of interatomic bonds. As a consequence, the magnitude of the elastic modulus is a measure of the resistance to separation of adjacent atoms, that is, the interatomic bonding forces. The bonding forces is a derivative of interatomic potentials with respect to the distance between atoms. Furthermore, the Young's modulus is proportional to the slope of the interatomic force separation curve as the equilibrium spacing. Through simple derivation, we can qualitatively determine the magnitude of the elastic modulus of sodium chloride. This is an example of the magic connecting the microscopic and macroscopic worlds. Up to this point, we have been talking about materials from a microscopic atomic scale perspectives. We discussed the interatomic forces, interatomic potential energy, and how elastic deformation corresponds to small changes in interatomic spacing. This gives us a very powerful physical picture. However, there is one practical problem. In most engineering situations, we cannot directly measure atomic scale quantities. We cannot easily measure interatomic forces or potential energy curves, or bond stiffness, especially for real engineering materials. So the natural question is, how do we obtain mechanical properties in practice? The answer is simple. We do mechanical testing. Mechanical tests, such as tension and compression tests, are the most direct and reliable way to obtain mechanical properties of materials. There are several main purposes. First, they allow us to obtain basic strength data. For example, how strong is the material? When does it yield? When does it fail? Second, mechanical tests are used to evaluate reliability. What we want to know whether a material will behave consistently and safely under load. And third, they are essential for failure analysis. When something breaks in service, mechanical testing helps us understand what went wrong and why. Mechanical tests follow standard procedures. The first step is specimen preparation. Specimens are prepared according to standards such as ASTM, ASME, or NIST. This ensures that results obtained in different labs can be compared fairly. Next comes loading. In a tensile test, we apply a continuously increasing uniaxial force to the specimen. The load is increased until the material begins to nag, or even eventually ruptures. At the same time, we perform data recording. We measure force and we carefully measure elongation or contraction, usually using an exometer. Finally, we perform post-processing. From the recorded force and displacement, we compute stress and strain and construct the stress-strain curve. This curve is one of the most important tools in materials and solid mechanics. At this point, it is important to connect back to what we discussed earlier. At the atomic scale, elastic deformation corresponds to stretching interatomic bonds. At the macroscopic scale, we cannot see atoms, but we can measure stress and strain. Mechanical testing allows us to extract macroscopic quantities that indirectly reflect the underlying atomic interactions. So mechanical testing is really the bridge between the microscopic world and the engineering scale behavior. Now, let's look at a specific and very important example, structural steel. The structural steel, also called mild steel or low-carbon steel, is one of the most widely used engineering materials. It is used in buildings, bridges, ships, towers, and vehicles. One of the key reasons for this popularity is that it is ductile. That means it can undergo significant plastic deformation before fracture. This ductility plays a critical role in structural safety. When we perform a tensile test on low carbon steel and plot stress versus strain, we obtain a characteristic curve. This curve can be divided into 4 distinct stages. Understanding these 4 stages is essential for engineering design and for interpolating mechanical behavior. Let's go through them one by one. The first stage is linear elastic region. In this region, stress is proportional to strain. Mathematically, we write sigma equals E times epsilon, where E is the Young's modulus. If we unload the material in this region, it will return to its original shape. There is no permanent deformation. Physically, this corresponds to small reversible stretching of interatomic bonds. The slope of this linear region is Young's modulus, which measures the intrinsic stiffness of the material. As we continue loading, the material reaches the yield point. At this stage, plastic deformation begins. For low-carbon steel, this is often accompanied by a yield plateau, where strain increases significantly while little or no increase in stress. This means the material can deform plastically without requiring higher stress. Microscopically, this corresponds to the onset of dislocation motion. Once yield begins, permanent deformation occurs. If we unload the specimen now, it will not return to its original length. After yielding, the material enters the strain hardening region. In this stage, additional plastic deformations requires increasing stress. The material becomes stronger as it deforms. This happens because dislocation density increases, and dislocations begin to interact and impede each other's motion. An important point here is unloading. If we unload the specimen during the strain hardening stage, the unloading path is elastic, with a slope approximately equal to Young's modulus. However, a permanent plastic strain remains. This is what we refer to as cold working. Eventually, the material reaches its ultimate tensile stress. Beyond this point, the specimen begins to nag. The cross-sectional area decreases locally, and deformation begins highly non-uniform. Although the applied load may decrease, local stress in the neck continues to increase. Finally, fracture occurs. This marks the end of the tensile test. This stress-strain curve contains a tremendous amount of information. From it, we can determine the Young's modulus, the yield stress, the ultimate tensile strength, the ductility, the energy absorption before failure. These are the quantities engineers usually directly use in design. So far, we have seen that elastic deformation is reversible and is related to stretching of atomic bonds. Now the question is, why does permanent deformations happen? The answer is dislocations. Let's look at the picture on this slide. A dislocation is a line defect in the crystal structure. It represents a region where the atomic arrangement is not perfect. When a shear stress is applied, the crystal doesn't deform by moving an entire atomic plane at once. It could require a very large stress. Instead, deformation happens by the motion of dislocations. In the top sequence of images, you can see how a dislocation moves step by step through the lattice. Each small movement only requires breaking and reforming a few atomic bonds locally. But after the dislocation passes through the crystal, the entire lattice has shaped by one atomic spacing. This results in permanent deformation. In the lower images, we introduce the idea of a slip plane and a slip direction. Dislocations move along specific crystalline graphic planes and in specific directions. On the macroscopic scale, this motion appears as slip lines on the surface of a specimen, which you can see in the experimental image on the right. Now, we understand plastic deformation and the role of dislocations. Let's take a closer look at how we describe deformation qualitatively. In particular, we need to distinguish between engineering stress strain and true stress strain. Let's start with engineering stress and engineering strain. In a standard tensile test, engineering stress is defined as the applied force divided by the original cross-sectional area. Engineering strain is defined as the change in length divided by the original length. These definitions are simple, and they work very well for early stage of deformation. In fact, for the elastic region and even the early plastic region, engineering stress strain is usually sufficient. However, something important happens once the material enters the necking stage. As you can see from the specimen image, after necking begins, the cross-sectional area is no longer uniform and no longer equal to the original area. At this point, engineering stress starts to underestimate the actual stress inside the material. This is why we introduce true stress. True stress is defined as the applied force divided by the instantaneous cross-sectional area. Similarly, true strain is defined as the incremental strain accumulated continuously, which leads to a log expression. The K idea is very simple. Engineering stress and strain use initial geometry. True stress and strain use current geometry. Before necking, the difference between engineering and true measures is very small, but after necking begins, the difference becomes significant. That is why if we want to study plastic flow, strain hardening, or perform large deformation modeling, true stress and true strain are much more meaningful. On the right side of the screen, I derived the relationship between engineering stress strain and true stress strain. I'm leaving this derivation as an exercise for you. Please be sure to try to derive it yourself after class. Here, we come back to the concept of Poisson's ratio. Poisson's ratio is defined as the negative ratio of lateral strain to axial strain. The negative sign simply reflects the fact that tensile tension causes lateral contraction. For most common materials, Poisson's ratio is positive. However, there is an interesting and important exception. Some artificially designed structures, often called some artificially designed structures can exhibit a negative Poisson's ratio. This means that when you scratch them, they actually expand laterally instead of contracting. This doesn't violate physics. It comes from their internal geometry, not from unusual atomic bonding. So if in the future you ever see a structure that becomes wider when it is pulled in tension, don't be so surprised. It is designed mechanical response, not a mistake. Up to now, we have mainly discussed materials like low-carbon steel, which show a clear yield point on the stress-strain curve. However, not all materials behave like this. So let's first look at a practical issue. What if a material doesn't have a well-defined yield point? Many materials, such as aluminum alloys, don't show a sharp yield point. Instead of a clear transition from elastic to plastic behavior, the curve gradually bends. In this case, we need a practical definition of yielding. This is where the offside method comes in. The idea is very simple. We take the elastic portion of the stress strain curve and draw a line parallel to it. Then we shift this line horizontally by a small specific strain value, usually 0.2% or 0.002 strain. The point where this offside line intersects the stress strain curve is defined as the offside yield strength. This definition is somewhat artificial, but is extremely useful. It gives us a consistent and reproducible way to define yield strength for materials without a clear yield point. In engineering practice, this is often the yield strength reported in material data sheets. Now, let's move on to a very different class of materials, brittle materials. Materials that fail at relatively low strain are classified as brittle. Examples include concrete, stone, cast iron, glass, and ceramics. If you look at the stress strain curves of a brittle material, you will notice several key features. First, the curve is mostly linear or only weakly nonlinear. Second, there is very little plastic deformation. And third, fracture occurs suddenly, often close to the proportional limit. This means that for brittle materials, failure is not preceded by large, visible deformation. There is little warning. There is why brittle fracture is often considered more dangerous than ductile failure in structural applications. Next, let's compare tension and compression, and how different materials respond to them. We start with ductile materials such as steel. In the initial stage, the stress strain curves in tension and compression are very similar. The elastic response is essentially the same. However, after yielding, the behavior becomes very different. In tension, ductile materials undergo necking and eventually fracture. In compression, they tend to bulge outward and often become even stronger as deformation continues. This is why ductile materials perform well in compression. Now consider brittle materials such as cast iron. For brittle materials, the stress strain curves in tension and compression have similar shapes, but the key difference is the strength. The compressive strength is usually much higher than that in tensile strength. As a result, brittle materials are often used in compression but avoided in tension. Concrete is a classic example of this behavior. Now, let's apply all of this knowledge to a simple structural design problem. In this exercise, we are given 4 structures. The cross-sectional area, the beam length, and the geometry are the same. With the only difference is which members are made of iron and which are made of steel. From the material behavior, we know 2 important facts. Iron is brittle and is best used in compression. Steel is ductile and performs well in both tension and compression. So, when we examine these structures, we should assign materials based on the type of loading in each member. Members that primarily carry compression can be made of iron. Members that carry tension should be made of steel. Using this reasoning, structure B and D are acceptable choices. However, there is an additional consideration. In future lessons, you will learn that compression members should be as short as possible to avoid buckling. Taking this into account, structure B is the most reasonable choice. Well, before the end of this lecture, I want to leave you a very interesting question is that why do wires, the electrical wires, have a service life, right? Usually these wires are made of metals and they are just metals without any organics. So why they have a service life? Think about this question and we will discuss it later in the next lecture.